All right, y'all. So today is the end of Unit 9. So the good news, looking at the roadmap, is once we finish today, you have a whole week to dance around with this stuff. And it's a long time before I lecture again. So this will be your last lecture chance to grip the Stoic steps if you haven't yet. But I haven't had y'all coming to tutoring, so I'm assuming y'all are doing really well. For those of you at home, pause the video, copy down that screen. Just like yesterday, today is another little tiny twist that you can be asked to do just in terms of drawing a conclusion when studying stoichiometry. So here's what the deal is. It turns out that there is no perfect system. All of the work that we've been doing on the whiteboards to find our theoretical yields, well, it's just that. It's theoretical. It turns out that if you were to take any of the reactions that we've done in my examples and actually do them, the amount you would get at the end wouldn't match the amount that we keep saying that you should get at the end. And that sounds a little weird because, well, what's the point of doing it if it's not the same in lab? Well, what happens is that when you go through the process of doing any reaction, there's always some energy lost to other places during the procedure. Maybe it's your fault, maybe it's just the fact that it produced so much heat that some of the energy went towards that instead of producing products. But anyway, every reaction, therefore, has two different values that you have to worry about. One of them being the theoretical yield, which you know how to find because we've done it a bunch. The other is what we call the actual yield. It's the amount that you, well, actually get at the end of a lab. So what you would do, for example, is if I said you mix A with B to make C, well, we can figure out on the whiteboard how much C you should have based on your starting amounts of A and B. That's a theoretical yield. But then when you go back to the lab area and mix A and B together and you have C, you could then go and put it on the scale. Let's say we went to grams and look at that amount. And now you've got two numbers, how much you should have gotten and how much you actually got. And what you can do is take those two numbers, plug it into that pink equation that I will give you on the test, where it's the actual yield that you got in the lab divided by the theoretical yield, what you should have got, times 100. And it'll give you a percentage of what percent you got of what you should have got. So the very best percentage would be 100%, but really in a lab, you're shooting for 99%. A good scientist will get at least 90% of their percent yield, in my opinion, at least. So what's fun about Monday's lab when you boil the acid and do the stuff that I've been mentioning is that at the very end of that lab, you're going to measure how much product you produce, and you're going to compare that to how much you should have produced, and we'll find out whether you suck at science or not. Because hopefully you get at least 90% of what you should have got. This is called percent yield, this idea. And before we jump into our two problems, again, we're just going to do two problems today. I would like to go logic on you one more time to make sure that what I've just said didn't go over your head. So take a look here. Don't write this down. But let's pretend that you're going car shopping. And we've got this car that's being advertised as 31 miles per gallon. Y'all are close to actually maybe getting to go car shopping if your parents let you. Or maybe they're just handing you one down. 31 miles per gallon, is that good or bad? Do you know? That's good. Yes, that's very good. My truck gets about 14 because I hate the environment. But yeah, I would kill to get 31 miles per gallon. But what that advertisement basically says is when you're at the pump and you put the pump in the car, for every gallon of gas you put in, the car should travel 31 miles. That's the advertised amount. You know how they come up with that number? How the car dealership people come up with that number? They look at the engine and they run calculations. And they say, based on the way we built this engine, theoretically, it should go 31 miles per gallon. But guess what? They're a bunch of liars. Because you know what the engine does while the car runs? What does the engine do in general? It gets hot, all right, which is a big loss of energy. There's other things that makes your gas mileage not be as good as it's supposed to be, like your air conditioning system and stuff like that. But it turns out that when you're driving it, you only get 26 miles per gallon. And instead of you getting mad at the dealer for lying to you, they're allowed to do this because they proved on their little whiteboards that the car should have went 31 miles per gallon. But when you actually drove it, it didn't. And now you've got those two numbers, right? You've got the theoretical and the actual. So what could we do to those values in order to find the percent yield? Well, what number goes on top? Look at your equation from a slide ago. Yeah, the actual yield. So what's our actual yield here? 26. So careful. So that's one of the problems you can run into on my problems, right? It sucks to have the two numbers but invert them because you'll get a different answer. Now, a good trick here is to realize that if you did the science right, that actual yield up top has to be smaller than the theoretical yield on bottom. So in other words, if you did everything right, the actual is always the smaller number. Not a bad note to have if you're good at notes. But anyway, actual divided by theoretical times 100. All right, can anybody run this for me real quick? What percentage is the car getting that it's supposed to get? It's a percentage, go 2 digits past the decimal. What'd you get? 83.87? Yes. All right, is this a good science car? I was above 90% would be the best if you were in the lab. As far as cars go, I don't know. This is cars are really not my specialty. This is just an analogy that you can usually understand. But yeah, this percentage when you're in the lab, you want it to be in the 90s. Otherwise, you've done things wrong. Thank you for that. The other thing the opening slide mentioned was the way these problems look when you run into them. And here's where you could have issues, because this is still just stoichiometry. But here's where you get confused. These problems, when it's a percent yield problem, they're going to give you two numbers. One of those numbers is the number you're always used to getting. It's the starting amount of a reaction. That number needs to go at the beginning of a grid so that you can run values on it. The other number they give you is the actual yield. Listen to this for a second. The only way to do a percent yield problem is to drive the dang car or to do the reaction. So if you're on Canvas just tearing through Cummings problems, you're not doing labs, right? You're just answering these problems that I've made up or stole from textbooks. My point is that if you don't drive the car or you don't physically do the lab, then you can't have an actual yield, right? That's something you get by doing. So if it's going to be a random chemistry question that you're asked to answer, they have to be like, Bob did a lab, and when Bob did the lab, he got this number. They have to give you an actual yield. The issue you run into is that when they give you those two numbers, one that goes into the grid and the other one that doesn't, it goes into this actual spot at the very end, is that you get confused on what number is what, and you put the wrong number in the grid, or you put both numbers in the grid, or you think it's a limiting reactant problem and you run two grids. That's from yesterday. Do you see how you can get your wires crossed? So you need to make sure that you're on top of what it's asking you to do. I'll show you what I mean. Are you ready? Maybe, oh, did I just stop my video because I'll be mad? Okay. Copy just the reaction, please. Just the reaction. Now, you'll notice that the problem tells us about my friend Betty. All right, that's kind of sad. Betty died from food poisoning a week after she did this. But I know, it happens. I've never met Betty. Betty did this reaction. And look, there's two values. Now, again, I want to make this point. Yesterday, when there was two values, we ran two grids. But this isn't asking for a limiting reactant. It's asking for a percent yield. So this isn't that. So don't get it mixed up. It says that Betty made X amount of atoms of cesium when she reacted this many grams of hydrogen. Find the percent yield. One of those two numbers is a starting amount, and the other number is an actual yield. Whatever number you think is the actual yield is a number that you set aside. You don't use it till the very end when you run that new equation that I just showed you today. Which one of those numbers do you think needs to go into our grid? The 2.36, because if you read your context clues, that is the starting amount when she was at the beginning of the reaction. She started with 2.36 grams. That down for my glare. Grams of hydrogen. Let's find out, with that starting amount, how much product should she have made, which is a theoretical yield, which is what we've been doing for days and days and days. All right, here we go. See, grams of hydrogen, right back to our steps. Can you start with grams of hydrogen? No, your starting must be moles of the same substance. Once you have moles of your starting substance, then you always go to what? To moles of the other substance. To moles, in this case, it's converting to. Now, we want our units at the very end of the theoretical to be in the exact same units as the actual. So just go look at that other number. That number that we set aside, you'll see that it's atoms of cesium. All right, so I could write that up here. If you go back and look, we've got, what's the number? 1.19 E24. 1.19 E24. This is just the data from the question. That's how many atoms of cesium that chick made in lab. All right, so we're trying to theoretically find those exact same units. You'll notice, though, that we're not there yet. All right, at the end of step 2, we always have moles. Sometimes we get to stop there. In this case, we don't, because we want atoms. So let's head over to atoms of cesium. And there's your big, beautiful grid. All right, I'm going to drag all the diagonals. Let's get Aspen out there. I love Aspen. 1/4. All right, let's go over to cluster 2. Talk to seat 1. Hey, 2-1. What number should go in that square? Very good. 2.016. All right. She knows that if it's not mole over mole, you use your conversion factors. Those guys right there, for those of you at home. In which case, it's 1 for mole, periodic table for grams, and there are 2 hydrogens, so we doubled the hydrogen mass. Right, let's go to cluster 3, seat 1. Hey, 3-1, what would you put in that square? The number 2 is correct. She knows that because it is moles over moles, in which case we always use the coefficients. And if you look at the original equation, you can see that cesium has a coefficient of 2. Therefore, for the hydrogen, I'll put a 1 because there's no coefficient in front of it. Go to cluster 3 again, this time seat 2 though. Hey, 3, 2, what would you put in that square? Avogadro's number, she said, because it is not moles over moles, so we use our conversion factors again. I'm going to draw a card for the answer to this grid. Watch your sig figs if I call on you. Let's go over to cluster 6. Aspen, stand by. Cluster 6, seat 6. Aspen, do you have an answer?
1.34 E24.
Did y'all get 1.34? You must have just split something because you're really close. I got 1.41. Is that what you got? Okay.
What's that root?
Why'd you give me your second answer though? All right, yeah. I get 1.41 E24 atoms. What's the vocabulary name of that orange number? Theoretical yield. The answer to any problem on a board or on your paper is always a theoretical yield. That's not what this question wants, right? What is the percent yield? So we go to our equation. We know that percent yield, actual divided by theoretical, times 100. All right? So here's the theoretical. Here's the actual. We didn't do a lab, so we had to take Betty's data. I lost my purple marker. I'm going to get it now. Okay. So let's do actual 1.19 E24 divided by theoretical 1.41 E24 times 100. And we'll find out if we should hire Betty in our lab. She did, but I like ghosts. I did something wrong. Oh, yep, I see it. Anybody want to share their percentage with me? Yeah, I get 84.4. So. Do you hope Betty's your unit partner on Monday? No, that chick spills stuff. Drinks it when you're not looking. Thus the accident. And that's the entire skill of the day. We have one more problem to do. What do you think? See how at the very beginning of the unit I said as long as you do the grid, you can do everything? All right, because these little extra steps at the end, those are really easy, right? It's just the grids that can mess you up if you're no good at stone. All right, I'm going to let you do the last problem of the unit on your own. I'm just going to give you a 1-minute head start before I tell you which number is the actual yield. Because remember, if it asks for percent yield and you didn't do a lab, one of the two numbers they give you doesn't go in the grid. I know I've said it a bunch of times, but it's because you won't believe how many times I say it. And there's still people doing awful things. Identify what number is what, and then let's start working towards your percent yield. Copy down, same thing as usual. Copy down the reaction, but not the question. Just extract your data. and you don't have to wait for me. If you can identify which one's the given to start your grid, then do that. Which one of those numbers is the actual yield? The 7,000, just use the context clues. Look, this was the amount that was made in lab, right? So my actual is 7,115 grams. 7,115 grams of copper 2 iodide. Copper 2 iodide. Don't put any of that in the grid. These are the units you need to end with, so the numbers can talk to each other when you do the final step. Use the other given to get a theoretical. Let me know if you get stuck. So far as make sure you end up with the same units as your actual. Yeah, I don't know that number on the top of my head, but it's correct. The other value is what you started with. Look, you did the lab this time, apparently. Kudos. But when you headed back there, you started with 25 moles of the copper 2 nitrate, and when you were done with the lab, that's how much product you made. Let's see how much you should have made. Good news or bad news? Moles is always good news. We get to skip step 1. We already have moles of our starting. We know that on any problem, once you have moles of the starting stuff, you always then go to moles of the other stuff. In this case, the CuI2 is what we want at the end. Unfortunately, though, we don't want moles of it. In order to compare to this 7,000 number, we have to have grams of it. So we'll do step 3, converting that to grams of the unknown. I'm going to drag my diagonals. Moles over moles is coefficients. The copper 2 iodide has no coefficient in front of it. The copper 2 nitrate doesn't either. They're both 1s. Grams over moles is conversion factors. What's the molar mass of CuI2? Anybody? 317.35. Can anybody second that? All right, sweet. So copper plus iodine is this number on the periodic table in the moles. All right, so really it's just that number times 25, it looks like overall. 7933. Okay, so careful though. There's only 3 sig figs here, right? You can get varying numbers if you don't do this part right. All right, so I can only have 3 sig figs there. So I'm going to round that to 7930. Everyone all right? I have a theoretical yield now because that's the answer to any grid. There's the actual yield, the value given that I've not yet touched. I know that if I go actual, this number, divided by theoretical, that's 7930, times 100. That's the equation. 7115 divided by 7930 times 100. Ooh, were you a good scientist? You're so close to having an all right experiment. Yeah, it looks like you only got, what, 89.72%?
Wait. With the honors boost, it would be a 90.
This is true. This is true. All right, you get to graduate. He used the multiplier to become a good student. And you have an audible yawn in like 10 minutes, so I guess something's going all right. Are there any questions? Computer data mark.